Welcome to the ePathshala lecture series on computer science for postgraduate students, and we are dealing with the subject computer graphics and visualization. We have had a few sessions earlier, around 9 sessions have gone, and we are in the 10th session in the lecture series. And in this series today, or in this lecture today, we'll be talking about 3D object representation, and in that specifically we'll be focusing on modeling using meshes, polygon meshes particularly. And let us also look into maybe some introduction to splines as well. So let us start with 3D object representations, and then we'll be getting into mesh modeling and further discussion on splines. We have been so far discussing on all the 2D aspects of computer graphics. From this lecture onwards, for few more lectures, we'll be talking only in 3D. That is, in terms of 3 dimensions, we'll be discussing anything in the context of 3D graphics. So how 3D graphics is different from 2D graphics. The other dimension, that is depth, is actually added. So we have got width, we have got height, and we have got one more dimension, the depth is added to any object that we discuss. So it is also true that in the real world we have no 2D objects. Any object is actually in 3D. So it makes more sense to talk more deeply and learn more about 3D than to stick to 2D. Some of the techniques that we have discussed in 2D graphics are as well applicable and can be extended for 3D graphics as well. For example, clipping, which we discussed in the previous session, can be as well applied into 3D. So the same 2D clipping like Cohen-Sutherland line clipping can be applied to can be extended to 3D clipping as well. So let us understand how the 3D world is and how to actually create 3D objects. So how to create 3D objects and represent them in a program, or maybe create them and see them visually and have a feel for 3D. So how do we represent objects first? So how do we first of all create a 3D object? That's the fundamental question. So let us understand the fundamental techniques to represent 3D objects. There are various techniques like using meshes, we call them polygonal meshes. Splines we can use fractals, we can use NURBS, so which are extensions of splines. We can use other simple techniques like particle systems. We can use maybe physically based modeling, and there are so many techniques that are used to actually represent 3D objects. Like extrusion is one important technique, a simple technique as well, and sweep representations and constructive solid geometry are also some of the examples of modeling in 3D. That is, these are the various techniques that we use to model 3D objects. So let us start with the mesh modeling, and with the first to start with, let us look into what mesh modeling is. Fundamentally, how do we create a 3D object? That's the question. So in computer graphics we have two basic schools of thought, or two basic ways to create 3D objects. Like either ways you can feel that the object is a 3D object. The first way is called as surface modeling technique, or it is also called as boundary representation. The other way is solid modeling and is also called space partitioning representation. Surface modeling is it can be understood like this. We try to model only the outer surface that encloses the object. That is, imagine you are trying to actually model only the outer skin or outer layer that covers the object. That means when we will not be actually modeling the inside of the object in surface modeling. So we will be modeling only the outer shell, or the outer layer, or the outer skin that covers the object. So when we try to model an object using surface modeling, we mean to say that it encloses some airspace within it, and so the object's outer layer is actually modeled and not the inside of it. So if we break open the object once it is modeled, what we will see is just empty space and nothing. So that is where surface modeling is all about. So try to model only the outer layer of the object that makes up the object. For example, if you can imagine say an orange, we try to model only the outer layer of orange. So that is that we peel it off and eat it, isn't it? So only the outer layer is what is modeled in surface modeling. And some of the best examples are mesh, spline, rotational sweep, translational sweep, fractals, and so on. The other modeling technique, which is solid modeling, is all about modeling not only the outside but also the inside. So basically model a complete pure solid. So it is also called as space partitioning representation. Because of the name, it looks quite tricky, so we will understand that later when we discuss what space partitioning is. So solid modeling basically attempts to model not only the outside but also the inside of an object. So it is always important, sometimes it is really important to understand what is inside. For example, if you imagine, if you create a solid ball or if you create a solid wood like object, so when we break it open, it is also wood inside, so there is some mass inside. So it makes sense when we create objects, or it depends again on requirements. Like if we want just only the outer surface and we are not breaking it up apart and we are not dealing with the inside, we can as well go with surface modeling. But if we want the inside as well, we can go with solid modeling. So you can remember these two techniques, and when we go further into details, you will understand better. So let us start with the first technique in surface modeling, which is mesh modeling. Mesh, we can also call it as polygonal mesh. Mesh is something like, it is a collection of it is actually many interconnected polygons or many interconnected triangles, maybe a mix of triangles and polygons connected. So we try to actually create the surface of the object by using or by approximating the shape using many connected polygons. We will be approximating the shape. Let me make it more clear again. We will be actually creating the outside skin, or we will be actually modeling the outer layer of the object by using many connected polygons. So we call that as polygon mesh. It is something like taking an object and wrapping around a kind of what is called a connected polygons, so that they make up the object. So here we can use many triangles, because triangle is the first level polygon or basic polygon, and the many other sides. If we use like more than 3 sides, we will be having other polygons. Okay. So fundamentally we can use either triangles or maybe other planar polygons. Whenever we talk about a polygon, we always assume that it is flat and perfectly planar. Okay. So if you look into the examples shown here in the slide, you have a fish modeled using polygonal meshes, and particularly the triangles. It is done with triangles. And the teapot, the famous teapot, that it is called as the Utah teapot, UTAH, the Utah state in US. A famous teapot is actually modeled using triangles, and again there is a sphere that is modeled using polygons. So we can model any object using meshes or using connected polygons for that sake. But as we know that because polygons are more flat and planar, maybe polygons are best suited for modeling objects like say tables, like flat surfaces like the benches, tables, the vertical walls, and any flat surfaces can be easily modeled using polygonal meshes, and they give the best modeling. They will be the best modeling tools for modeling flat faces or flat surfaces. But if we try to model surfaces which are spherical, which are curved, which are like irregular, we will be like having an approximated surface but not the true spherical surface. For example, take sphere. If you try to model the spherical surface using polygonal meshes, what happens is, if you look into the slide there, the shape is as if like it is your football like shape, but more approximated polygons or more closer polygons are there which make up the spherical shape, but it still looks like what is called a tessellated, or we call it tessellation, or we call it it's like a buckyball or your like football like shape. And this we call it because we try to use polygons that are flat and planar to model surfaces which are not flat or planar. So that's the interesting point here. So we are trying to model non-planar surfaces using flat planar polygons. So that's fundamentally is the critical issue here, that is we get an approximation to the underlying surface and we never get the true surface. And what happens is, if you have to get a true approximation to the underlying surface or the underlying spherical or curved surface, we will be using too many polygons and which are smaller in size. So I hope you understood this point. Like if you have to have a better approximation for objects that are non-planar or curved, what we can do is we can model them using smaller infinitesimally thin polygons, and we can have many of them. But what's the problem? The problem is we have too much of data. So for each polygon we will have to store a lot of data. So and instead of having say a number of few polygons, if we have too many polygons and we have too much of data representing one single spherical or maybe curved surface. So that's fundamentally the maybe kind of drawback with flat polygonal mesh modeling. Okay, let us try to understand how these polygonal mesh data is stored, or maybe how do you represent an object using polygonal meshes. If you take a cube like object, for example, cube has got perfectly flat planar polygonal faces. So modeling the outside of a cube, the skin of a cube, using flat planar polygons or maybe polygonal mesh is actually much more easier, simpler, and at the same time it gives a perfectly perfect cube object. So the data that corresponds to a polygon is like vertices. Vertices are positions in space, and then these vertices are connected by edges, and as you can see in the diagram here, vertices are connected by edges, and these edges make up faces, and many faces together make up polygons, and the polygons make up surfaces, or we can call a face as a surface also, but all surfaces are not faces. Okay, because a face is understood to be a triangle or it can be a polygon. Okay, here these are all closed faces, so no open faces anywhere, and these together make up one surface. And for the cube there are 6 surfaces, and when these 6 surfaces are put together, is if we have to create a data structure, or we have to find out what are the vertices and how these vertices are connected and how these edges are connected and how the edges make up a polygonal face and how various polygonal faces are connected. So if we have data that is representing these vertices, edges and polygons, we can store them conveniently in a table called a geometric table. We can call it as geometric data. We can also store them in a kind of list. So we can have geometric data or attribute data for a polygonal mesh. Geometric data for a polygonal mesh representing an object corresponds to vertices, edges, polygons and surfaces, whereas attribute data for a polygonal mesh corresponds to the color of a particular face, maybe the texture and maybe the kind of light and so on. So other kinds of things are called as attributes. geometric attributes correspond to its position, its orientation of the polygonal mesh. So when you have to maintain data corresponding to a polygonal mesh that is being used to model a 3D object, we will be storing them in various lists. We call vertex list, we can have edge list, we can have face list, we can have one important list that is not discussed so far, which is normal list. So if you can see the a diagram here, it's a shape which is like a hut like thing, like a home like thing, and it has got say vertices numbered from 0, 1, 2, 3, 4 until 9, and it has got maybe various edges. So vertices will be connecting, the edges are connected by vertices. Okay, the vertices are connected by edges, and many edges together make up a face. Okay, so now you might also see that there are n1, n2, n3, n4, n5, n6, and so on. They are actually the normal vectors. A normal vector is a direction which is perpendicular to the polygonal face. Okay, so it is important that we also store, we also have maintain a normal vector list, which is important for one reason, as you can see here in this slide. Along with the geometric information like face list, vertex list, edge list, we can also maintain normal vector list. Why is this important, you can ask? The normal vectors actually identify the orientation of a polygonal face with respect to a light source. How is that? How does that make sense to you? Let us maybe elaborately discuss. For example, there is a light source. Okay, so the light source is actually falling on the object. The light source is there somewhere, it is falling on the object. Now if the object is oriented towards the light source, then the object or the face of the object should be well lit. It is obvious that if the face of a particular object is oriented towards the light source, it should be well lit. Any face of the object that is oriented away from the light source should not be lit well, so relatively well. So that means how a face is oriented in the 3D world can be understood from the normal vector that we create for that face. Okay, here I mean to say by face, a face is a flat planar polygon. The planar polygon is actually, it's any direction that is perpendicular to the flat planar polygon is identified to be its normal direction. So we will be computing the light source direction and the normal direction, and we will be taking the angle between the two, and by that we will be able to compute in what direction the face is oriented with respect to the light source. Thereby we will be able to find out how much intensity, with what intensity the face is to be lit with. So that's fundamentally important when we deal with many objects in the 3D world, and there are light sources illuminating the 3D objects, and say we will have to compute how much of light is incident on a particular face. So maybe all of you might have heard names of 3D modeling tools like 3D Studio Max, Maya. I got tools like Combustion. So there are many 3D modeling and animation tools that you might have heard about. In open source, we got a tool like Blender. So all these tools let you create 3D objects and then orient them and then position them and then create all the lights, create all the various textures, create say for example various other objects, maybe other reflective, highly reflective or transparent objects. So you can drag and drop many basic 3D objects, and you can do n number of things with 3D modeling tools. And we are trying to understand how a tool or like 3D Studio Max or Maya does this job. So we are trying to understand the background theory of 3D objects. Now the normal vector, as you can see here, it's the normal vectors are indicated with the numbers 0 to 6 because there are 7 faces, and For the faces, you can see the normal vector components are 1 0 0 0 0 1 and so on. So we can compute normal vector to a particular face by taking by taking two vectors on the polygonal face and then taking a cross product of them, and the cross product will give the direction which is perpendicular to the plane containing the two vectors. So how you can compute normal vector is by take any two vectors on the polygonal face and then do a cross multiplication, and whatever you get is actually the normal direction that is perpendicular to the plane containing the two vectors. So that's how we can compute normals, and it is so important in 3D modeling. That's about the mesh modeling or mesh model. So much of so many 3D animation movies happen actually using mesh models, or mesh models are created because they are very simple. They are flat planar polygons, you can store them easily, the data structure is very easy to represent, and it consumes less time and volume. So obviously they are the most sought after tools for modeling 3D objects. The other tools that we can look into for modeling 3D objects using surface modeling are splines. Splines are actually purely mathematical objects, and splines splines are actually more fundamental in the sense they can be used to model 3D objects which are flat, planar, and also which are very much curved and which have a lot of curves and maybe a spear like or maybe very curvy. So these surfaces we can model using splines. Splines, if we start with, we can talk about fundamentally the Hermite splines, then we'll be talking about Bezier splines, and then we'll be focusing on basis splines, and lastly there are NURBS, which we'll not be discussing at depth because NURBS is an extension of basis splines. Splines, even in CAD design, even in automotive design, everywhere splines are used, but not as curves but as surfaces. So first we will be talking about spline curves, and then when we extend spline curves in two different directions, we get a spline surface. So for example, we can model a cloth with spline surface. We can model water with spline surface. We can model wavy objects or curvy objects with spline surfaces. So we can create a spline surface and we can wrap the spline surface around any irregularly shaped object. So spline surfaces are most commonly used 3D modeling tools which are meant for what is called surface modeling. Okay, if you look into the definition that makes up a spline is any composite curve formed with polynomial sections satisfying specified continuity conditions at the boundary of the pieces. Maybe it's a big definition. Let me read that again. Any composite curve formed with polynomial sections satisfying specified continuity conditions at the boundary of the pieces. So basically a spline curve is not a single curve, it is many smaller curves attached together end to end will make up a spline curve. So let me repeat that again. A spline curve is not a single mathematical curve. Basically it is made up of many smaller curves, that is, we will be taking many smaller curves and we will be joining them end to end to form a spline curve. So spline curves are fundamentally a piecewise polynomial sections of many curves which are pieced together to form a single continuous smooth flowing curve. So the first spline curve that we will be discussing here today is the Hermite spline. Okay, followed by that we will be talking about Bezier spline, and in the next session we will be talking about Bezier spline, and later about basis splines. So let us look into some terminology maybe to familiarize you with the topic. The splines have got terminology like parametric forms. So we'll be using parametric form to represent a spline curve or a spline surface. control points, convex hull, boundary conditions, order and degree are for polynomial functions. We know that we have got order and degree. Degree is the highest power to which the variable is raised, and order is actually always one higher than the degree. Okay, and approximating and interpolating type of splines, blending functions. The word blending functions will be often discussing in splines. Local control is a concept, is a kind of feature of splines, and basis splines, the Cox-de Boer recurrence relations, based on which we will be formulating the spline equations. So, let us look into the parametric form for how to represent a spline using parametric form. I hope you remember the discussion on say using Liang-Barsky line clipping procedure, where we have understood how to represent a line in parametric form. Here we are going to represent a curve in parametric form, and the curve is expected to, or is assumed to be lying in the 3D world. So, that means it will not only have, it has got x, it has got y, and it has also got a z. So, and the parameter being u. So, u is always the parameter, as we know that the parameter u ranges in the interval 0 to 1. If you remember the discussion on parametric form for a line, when we discussed about Liang-Barsky line clipping procedure in the previous lecture session. So, how to represent a spline? If you look at the equations shown here, let x of u and y of u and z of u be 3 variables, and u is the parameter. So, which is represented by ax u cube, bx u squared, and cx u and d. The components ax, bx, cx and dx are the coefficients, and y of u similarly is represented by ay u cube, by u squared, cy u and dy. So, these are the components of the y parametric form for y, and the parametric form for the z is represented with az u cube, bz u square, cz u plus dz. And now a curve p of u is a function of a vector u cube, where a is the a vector and whose components are ax, ay, az, and b is b vector whose components are bx, by, bz, and similarly c and d, and a u cube plus b u squared plus c u plus d. If we look at the equation that makes up the spline curve in parametric form, the degree of this curve is cubic, that is, it has got a degree 3. 3 is the degree for the parameter u. So, we can call this as a cubic curve. So, a cubic curve in parametric form can be represented with the equation p of u, where u is the parameter, is equal to a u cube, b u squared plus c u plus d. And let us see how the splines are represented in various types of splines that we have, that we can talk about. Splines can be categorized into 2 types fundamentally. One is interpolating splines and the other type is approximating splines. What are interpolating splines and what are approximating splines? If we can look at here, interpolating splines are those splines that touch all the control points, so that have to exactly pass through all the control points, while approximating splines are those splines that need not pass through exactly all the control points. Actually, what are these control points and why should a spline pass through? You might have this question now. What are these control points, and suddenly they have come. See, how do we design, or how do we create a curve? The shape of the curve is what we have to decide. So, it is that we wanted to decide the shape of the curve. We did not want to take some curve that is generated by a mathematical equation. We wanted to generate a curve of our own. So, how do we generate a curve of our own choice? So, for this we are going to place positions, or we are going to place a sequence of points in space, so in some order, and we want a curve, or we want to derive a curve equation that either approximates or that either interpolates these points, and these points that are going to define or that are going to control the shape of the curve are called control points. If you look at, maybe you can recollect in our day to day life, we've got rangolis, we've got columns. These things, I think you might have noticed that during occasions, festive occasions, the household, the ladies, they will be actually putting these rangolis or columns, like they put a lot of dots, and they try to approximate these dots with curves, so with various shapes of their choice. So that's basically a spline curve. Fundamentally, we want to define our own curves, and we are going to place some points that are going to direct that are going to control the shape of the curve, and these points are control points. And if a curve has to exactly touch and pass through all the control points, they are interpolating splines. And if the control points are just to be approximated, that is, the curve should still follow the path but need not necessarily touch these control points, and we say that kind of splines are called approximating splines. And we have examples for interpolating splines, which are Hermite and Cardinal, and we have got Bézier's, bases, and NURBS. Fundamentally, many of the popular spline curves are approximating splines only. So as I said, a spline is basically a combination of many curves. That is, you will be joining too many smaller curves to make up a spline curve, as we discussed before. But how do we ensure that where they join, that is, they are joining end to end, how two curve sections, when they are joining at some point, how should they join, or like in what manner they should join, what is the degree of each of these curves, should they have same degree or they are of different degrees, and with what smoothness they should join at the boundary, should they join smoothly or should they just join at the boundary, and there are so many questions. So we will be actually basically taking many smaller curves and we will be joining them at the boundaries end to end. So for that, we have got to estimate or to check whether the curves are joining smoothly. We can check C0 continuity, C1 continuity, and C2 continuity, that is C squared, C0, C1, and C squared continuity. The 0th order, the first order, and second order continuity. Two curve sections satisfying C0 continuity are like this, as shown in the first picture, which is the curves just meet. So it is something like one point is common for both the curve sections. They may be two different curves or two different things, but they are just joining at a given position end to end. And if they have to satisfy first order parametric continuity, the tangents to the two curve sections at this boundary where they are joining should be equal. Let me repeat that. So if two curves have to join a bit smoothly at the point at the boundary here, the tangents to the two curve sections at this point must be equal. And any two curve sections satisfying C square continuity look as if they are not actually two different curve sections, but they are actually one single curve sliced up and then joined together later. So imagine you got a single nice flowing curve, and now you are slicing it up and then again joining it together. So when two curves satisfy the C squared continuity, we mean to say that they are joining very smoothly at the boundary, and the curvatures of the two curve sections at the boundary will be equal, and the curvatures here means their second derivative. So you will be taking the second derivative and for the two curve sections at the boundary, and if they are equal, we say that the curvatures are equal, and we feel as if the two curves are not from two different families, or they belong to one single family of curves. So they gel up very smoothly at the boundary. The types of splines, as you can see here in the slide, there are say 4 control points, P0, P1, P2, and P3, and you can see a dotted line, so connecting P0, P1, P1, P2, P2, P3, and that line is called a polyline, and the spline curve is actually this a smoothly flowing curve from P0 to P3. There is another example shown here which has got 4 control points again, P0, P1, P2, P3, and these control points are given a serial sequence number, and as you can see the spline curve follows that order. So order is very important. So when we place points, we should mention the sequence in which the spline curve should take, the sequence that spline curve should take, or either it is an interpolating spline curve or it can be an approximating spline curve. The sequence is important. And that with that we come to the summary of this session. How to create, this where we have learned how to use mesh models for objects, as we have understood that mesh modeling is one of the easiest and simplest techniques to model the outer surface of any object. But when we try to model spherical surfaces or maybe surfaces that are not flat or planar, we get only approximation. We tend to see only approximated shapes but not the true shapes. We have seen the lists that are used to represent the mesh, like vertex list, edge list, face list, normal list, and from there we have moved to splines, and introduction to splines is what we have learned in this session. Thank you.